Okay, in this video we're going to discuss limits at infinity. We'll start with an example. So let's consider the function 1 over x as x gets larger. Okay, we'll make a table to analyze this function. So we'll have one row here is the inputs. We're going to put in 1, 10, 100, and 1,000. And then we'll put the outputs. So if we put 1 into this function, we get 1 over 1, which is 1. 10, we get 1 over 10, and then 1 over 100, and then 1 over 1,000. Okay, so you can see as x gets larger, one way of saying this is as x goes to infinity, 1 over x gets really small. It's getting closer and closer to 0. And one way of putting this notationally is to say the limit as x goes to infinity of 1 over x is 0. Graphically, what's happening is we have a horizontal asymptote. So if we put 1 into this function, we get 1. If we put 2, we get a half. If we put a half, we get 2. So we have this function that is getting closer and closer to 0 as we go further and further out. Okay, so it has a horizontal asymptote, y equals 0. Okay, so let's write down a couple general facts, and then we'll do a few more examples. So these are facts that we can use to do limits involving infinity. So the first fact is that if we look at x going to infinity and we have a constant, that's just going to be a constant. Constants don't change with respect to limits. And the second fact is if we take the x going to infinity and we have c over x to the n, this is going to be 0 provided that n is positive and an integer. And this is also true when x goes to negative infinity. All right, so we're going to use these facts to compute some limits in these following examples. So the next example here, we're going to use these facts to compute or calculate the limit as x goes to infinity of x squared plus x all over 3x squared plus 1. And there's a hint here. Divide every term by x squared. Okay, so we're going to follow the hint right off the bat. We're going to start this by dividing every term in the numerator and denominator by x squared. Don't know why we're doing that. We're going to do it just because the hint suggested us to do it. Suggested we do it. So let's simplify. So the first term, when we divide it by x squared, it becomes 1. Second term, if we simplify using exponent rules, we get 1 over x. Bottom first term is 3, and then 1 over x squared. Okay, so now we can go back to the facts we listed earlier. The second fact says the limit is c over x to the n equals 0 when n is a positive integer. So in the first, in the numerator here, we have 1 over x. You could think of n as being 1 in this case. So this 1 over x, this is going to go to 0 as x goes to infinity. And the 1 over x squared is also going to go to 0 because n is 2. That's a positive integer. Okay, and so then what we're left with is 1/3. And that's the limit. Okay, let's do another example. Let's find the horizontal asymptote of f of x equals x plus 3 over x squared plus 4. We saw earlier that really finding horizontal asymptotes is taking the limit as x goes to infinity. So we're going to take the limit as x goes to infinity of these of this function. We're going to use the hint from earlier. We're going to divide by x squared. In general, you should think of this hint as you want to divide by x to the p, where p is the highest power in the function. Highest power of x in the function. Okay, so 2 here is the highest power of x, so we're going to divide everything by x squared. Again, we'll get something that looks like this. And then simplifying, we get 1 over x, 3 over x, plus 3 over x squared, 1 plus 4 over x squared. And then every term except for that 1 goes to 0. And we're left with 0 over 1, which is just 0. So here we see that y equals 0 is the horizontal asymptote. What this function approaches in the limit is 0. All right, I hope you found this video useful.